A good party should be. Ooh, all right, so you're welcome. Oh, Nick, you cracked me up. I understand, I do, but anyway. We had to take the first derivative. I'm still recovering a little bit. Okay, we need to take the first derivative, right? ddx. ddx, both sides. Both sides. Why is that so important? Because the derivative of 5 is, whoo, did anybody write 5? Okay, what's another common mistake? Just in the first derivative, and we have to find the second. What's another common mistake? Not seeing the product rule. Whew. Second, d first, plus, wait, where's the dy dx? It's in the second one, not the first one, because wouldn't this one be an x prime, because you're deriving the x expression? And what's x prime? Just 1. Where's dy dx come? Right now, because first, d second, derivative of y is dy dx. Is that good? It's only there, not there. And it's not here either, because the derivative of 4x is negative 4 times x prime, which is just 1. Which is just 1. So if you guys, I should say, simplify properly, I believe you should have added the 4, subtracted the 2xy, and divided by x squared, which would give you, double check me, because I'm doing it fast, this expression. Nice? Is it okay? Why is it a little bit sad, though? Why can't I box it and be done? All right. So second derivative, what do we have to do now? Quotient rule, because I have to take the derivative of both sides again. And what happens when you take the derivative of the derivative? You get the second derivative. So therefore, we get d squared y. Are we getting the notation okay? Over dx squared. Bottom d top. Bottom, x squared. D top, derivative of 4 is just, but in the d top, what do we have? Oh, snap. I'm going to go ahead and make that little negative be on the outside. That's a little dangerous, I won't lie. If it was me, I probably would have made it plus, and actually, I'm going to just do that. I'm going to do plus a negative and make the 2x a negative. In my mind, it makes it a little bit easier and saves me from making mistakes. We are very prone to mistakes. We got to be careful. Oh, life lesson. Second, d first, negative 2, x prime, just 1, plus first, negative 2x, d second, dy dx. Did you guys get it? Bottom, d top, you have to remind yourself, where are you? I'm in the quotient rule. Where in the quotient rule? Bottom, d top, minus quotient rule. Top, d bottom. What's the derivative of x squared? 2x times x prime, just 1. I don't think I needed that, but that's okay. All right, bottom d top minus top d bottom all over bottom squared. X squared squared is x to the 4th. Did you do it? Good, you're welcome. Okay, so as we check this guy out, stick it to the man, box it, and you're done. That would be horribly wrong, because there's somebody in there that needs to be substituted for, that is not proper yet. Who doesn't belong? dy dx. Who is dy dx? This guy is dy dx. Plug it in, plug it in. Now pause. Does that make sense? We had a dy dx. We couldn't leave it there. We need the derivative at least in terms of x's and y's, if not all the way in terms of x's. Remember, in the back of the book, it's not always reasonable to get it in terms of x's. So you get a correct answer for whatever's being asked, then go try to make it match. Sometimes you'll be good. Sometimes you'll have to change things up a little bit. So when we simplify, we end up with, because I'm trying to make it match now. Oh, not even that. I still have to plug in. All right. Is there anything in common? I see an x in common. Would you guys rather pull out an x right now or just distribute everything? Okay. So if we just distribute, we get negative 2x squared y. I'm bringing that guy in. And then we get minus 2x cubed times dy dx is 4 minus 2xy all over x squared. Oh, that's nice. Those x's can reduce, yeah? And then minus, okay, and then we have 8x minus a negative, which would be plus 4x squared y all over x to the 4th. Do we even have to simplify our complex fraction? Because check it out. Dun, dun, dun. He's gone. And now what do we get? You guys said to distribute. I'm just going to keep distributing. I think it's easier, right? So yeah, we get the negative 2x squared y. If I distribute this guy, that'd be minus 8x plus 4x squared y minus 8x plus 4. Whoa. Do you guys get that? I think I have some like terms. What do you think? Yeah, I have a 4x squared y and a 4x squared y, which is an 8x squared y minus a 2x squared y, which would be a 6x squared y. I have a negative 8x and a negative 8x, which is a negative 16x all over x to the 4th. I do believe we can pull out a 2x, which would be 3xy minus 8 all over x to the 4th, which one of those x's can reduce. We end up with 2 times 3xy minus 8. If someone caught a mistake a long time ago, I'm going to be very sad. Did anybody beat me there? Oh. Has anybody followed the steps to where you agree? Not just out of blind faith, which is so dangerous life lesson. Two x times 3xy minus 8 all over x cubed, yeah. It's an x cubed after the x reduces? Uh-huh. You know what's super nice about the directions? They say in terms of x and y, so we don't even have to feel the pressure of trying to substitute. But can I show you guys really quickly, even though it doesn't apply in this problem, one last thing that you should check for before being done. One last thing that you should check for before being done. And in homework, if you don't check for this, some miracles are going to seem to happen, but they're not miracles, they're just math. But if you don't think to look for this last thing, you're going to get a little bit blindsided by a couple problems in homework. Technically, when you get here with x's and y's, what you should do is go all the way back to the beginning. We already used dy dx as this guy and plugged it in, but what we didn't do is look back at the original clue and say, hey, would this come up at all? Could I use this at all? What you would need to do is look and say, wait, is there any expression that looks like x squared y minus 4x? Do you guys see any x squared y's minus 4x's? No. No, I mean, I guess I could have kind of done a little bit of magic here with this x squared y minus. Maybe I could have done a few of them here. If this matched up anywhere in our answer, we could take this out and plug in a 5. And so it's going to look like magic if there ever was a way that it could connect to the final answer, and it would look like magic. What I mean by that is if I was to look right here, and this is going to look really, really weird, and I don't think they would have done it in this example, but if I take this version of the answer, I could actually have 4 different, it's going to look weird, x squared y minus 4x's. Check it. 4x squared y minus 16x. That's that and all of those but 2. Why on earth would I have done that weirdness? Split 6x squared y into 4x squared y and 2x squared y? because then that gets me the original expression, and the original expression can become a 5. So then 4 times I could plug into this one. It doesn't work in that one right here after I simplified. But I could substitute that expression for a 5 because of the original relationship that was given to me. And I could make this 20 plus 2x squared y all over x to the 4th, which you could pull out a 2, but that's about all you could do. Here's the craziness. These are both equally correct. But they look so different. In homework, you might have an answer. It might be totally right, and you check all of your work, and you're like, I don't get it. It looks nothing like the answer. Maybe they were able to use the clue to rewrite. Now, once again, this is way too complicated. It doesn't fit nicely into the answer at all, so I doubt they would have done it. I'm almost positive this would have been the preferred solution for this problem. But I just wanted to show you guys the idea that depending on the answer, if there is a way to plug in the original clue to make it simpler, they will. And it's going to look like magic even though it's not. Does that kind of make sense? Okay. So yes, we can plug in, and we need to plug in. We have to plug in the first derivative, dy dx, at some point whenever taking the second derivative implicitly. But there also is that original clue that can get plugged in. So guys, yesterday at the very end of class, didn't we write down steps for the second derivative? ¿Dónde está? Aha! So real quick, it's just a homework help. It's just a homework help, right? We talked about yesterday how with implicit functions, they can say find the slope, and we're like, oh, we've been there, done that. Oh, it's a little bit harder, okay. They can say find the tangent line. Oh, it's a little bit harder, but we can do it, okay. They can say figure out where the tangent line is horizontal. Okay, find dy dx set equal to 0. Where the tangent line is vertical, okay, find dy dx set the denominator equal to 0. They can ask us all the old questions we've seen, just now the functions will be a little bit messier, but here's something else. They can ask us for the second derivative. But I took some notes on this one, not because I know or think you guys are confused about what the second derivative is in general. You go again, you derive again, but I think it's helpful to have the steps of you take the derivative as is, you get dy dx, you derive as is again, both sides. But here's why I put the clue. You need to plug back in dy dx from step 1. That's exactly what we just did. You need to plug back in dy dx from step 1. And then simplify. And simplifying can take two forms. Simplifying can be good old-fashioned algebraic factoring, simplifying, combining like terms, bless you. Or, and/or. Quick little hint. Sometimes, just for simplifying, sometimes there's more than algebra at play. Sometimes can substitute in the original equation. Sometimes you can substitute in the original equation. Which, the last example, when I did that, it didn't really make it simpler. So it's like, well, what was the point? But if you look at the example we ended with yesterday, if we can make an x cubed plus y cubed a 1, man, that could make it look a lot simpler. If there was an x cubed plus y cubed. But if I zoom out, in the derivative, oh, did I not finish simplifying my complex fraction? Here, let me make it a little bit bigger so you guys can still be writing. I see a few of you guys taking notes on the top. Let me finish that final answer, simplifying that complex fraction. Let's get that, let's get that, let's bring them in just a little bit. Let's see if we get any x cubed plus y cubes, because that'd be kind of nice. All right, what do we get? Ugh. Well, we get a negative 2xy to the 4th that y squared is going to reduce with him. So then we just end up with plus 2x to the 4th y all over y to the 6th, double checking, negative 2xy to the 4th, minus, no, plus 2x to the 4th y. Yep, that's good. Double checking my signs really quickly. Ah, bummer. We almost had it. I'm trying to check. Why would it be a negative? No, it's okay. I would love for it to be a negative. If it was a negative, life would be so nice and pretty and neat. Doesn't mean it should be. Just double checking everything. So that's definitely a negative. Top, d bottom, bottom d top, minus top. I did make a mistake. Hold on. Double check me. Bottom d top, right? Minus top. That should be a negative, yeah? Minus top. Minus top. Yep, that should be a plus. Some of you might not realize how I knew that that was messed up. You'll see it right about now. Not that it always needs to turn out pretty. Why is the final answer negative 2x over y to the 5th? Magic happened. That doesn't make sense. How do things just disappear? What can this guy become? Just 1. Dun, 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 dun. The y is reduced. But it's going to look like magic. You're like, it doesn't make sense. You might have a perfectly correct answer, and yet, if you don't go back to the very beginning and see if there's some sort of random relationship, I mean, it was what the whole problem was based on, but a relationship that you can use to substitute, you might not have any clue how it got there. Does that make sense, how it might get weird? If you didn't go back to the beginning, that looks like a complete voodoo's going on. Mathematical, ooh, but nope, just a substitution. That's it. Done, done, done. Second derivative, done. Now that we've seen implicit differentiation and second derivatives of implicit differentiation and the fact that we can take derivatives of both sides as is, we are ready to go back to logarithmic differentiation. And this is what was at the end of homework that you might not have been ready to totally tackle. So that's why I'm giving you full credit if you did at least 3/4 of homework last night. Because I believe at the end of homework, were there really nasty functions? Were there really nasty functions you were supposed to derive? And I think they might have even said something about logarithmic differentiation. You'll remember what it is as soon as we... But some of you guys might be like, yeah, it was really weird because they mentioned something about logs and there weren't any logs. Silly book. I think they're going senile. Whoever was writing these problems. Unless, when they say logarithmic differentiation, they're telling you you can bring in an ln and it might make life better. Bring in an ln. We hated logs ever since pre-cal and algebra 2. Why on earth would we put a log if there isn't one? Yeah, to get rid of something you don't want, kind of like building bridges. Wouldn't this be a fun derivative to take? Make this to the 1/3 power and then do a u prime? But wouldn't it be nicer if we could just maybe ignore the... Where'd the root go? He's right there. No. Oh, Because a cubed root is the same thing as a what power? 1/3 power. And a log of something, some argument to a power, what can I do with pre-cal? This has nothing to do with calculus. With pre-cal, bring it down in front. And now that I have it brought down in front, I'm not scared of this guy because I can just take d dx at both sides. I don't care that there's an ln. No, take d dx. So what's the derivative of ln of y? What do you guys think? 1 over y. Good, 1 over. But don't forget your y prime. Good, your y prime. Equals. What can I do with the cubed root? Oh, he's just a 1/3 constant multiple. No stress. 1/3 times. Now pause. I still have to take the derivative of the ln. How to take the derivative of ln of u? 1 over u, 1 over the blop, times u prime. Okay. Oh, what's the derivative of 2? 0. What's the derivative of? It's okay. Derivative of tangent, derivative of the outer, secant squared of, good, keep it the same. Why am I doing another times? 1 over u, secant squared, prime. I had a u and a v. For my kiddos that like writing it all out, you could have said that f is equal to 1/3 ln of u. U is equal to tangent of v. V is equal to x squared, if that helps. So 1/3 times 1 over u times secant squared of v times 2x. Boom, boom, boom. You're done. Not get dy dx by itself. So does it make sense why this, oops, yeah. What did I just do? Yeah, but not. Think, to get dy dx by itself, what did you have to get rid of? And when you times y on both sides, since that's the only y in the entire equation, couldn't you have gone back and said, hey, who are you? What did I do? Plug him in, plug him in. And some of you might realize there actually is another way of writing this, because if I have this guy to the 1/3 up here and this guy to the 1 down bottom, I can combine like bases raised to power by subtraction. So technically, I would end up with this guy. 1/3 minus 1 is -2/3. -2/3 pops them down in the denominator with a 2/3 power. Which would have been the exact same thing if you had done the chain rule up above, brought down the 1/3, made it a -2/3 times u prime, which would be secant squared of x squared times 2x. Now, if you're really good at chain rule, you could have gone from here to here, no problem. But if they say to use logarithmic differentiation, maybe they're preparing you for harder ones, or maybe they would have stopped here, and you wouldn't have even had to do that jump. But this guy wasn't too awful to begin with. He was a little messy. But a reminder that if they're talking about logarithmic differentiation, what they're saying is if there's an ln, use properties. If there's not an ln, put in an ln, use properties. And all of a sudden with implicit differentiation, I'm not scared of an ln of y. I know what to do with him. Just don't forget to move the y to the other side to substitute and then simplify. So ready, set? Woo. Go. Quotient rule with the product rule. Wait. Why are they telling me logarithmic differentiation? Because life will be so much nicer if you put in an ln. Who knew ln was going to be a friend? Ready, set, go. Who knew ln was going to be a friend? Well, I did kind of hint at it last year, but Ready, set, go. Okay, check in your groups real quick. Collaborate. How are we doing? See if I can Mr. Che. No, I'll have to practice. Why am I doing times ones? Just to remind you that technically it's a 1 over u times u prime, but who's u prime? Just 1. Who's u prime? Just 1. But if it was 2x minus 1, ooh, if you had forgotten your u prime, things would have died. Why subtraction? Oh, you forgot that one? Oh, that's awful. Although remember, if it was 1 over, wait, couldn't you have made it to the negative 1/2 power instead? Contemplate. I'm moving the y. And I have 1 over x plus 3 over minus 1 over. What am I going to do? Now, is this answer going to look exactly like what you would have gotten if you had done the chain rule? Only at the very back, no ln's. Would this look exactly the same? No. Because way back here you would have done quotient rule. And quotient rule would have gotten you one nice, after a lot of simplifying, top and bottom, one nice big old fraction. What's true right now? We have 3 little dainty separate ones. So how could you compare? If you were to decide to use logarithmic differentiation to be kind of lazy on a nasty chain rule, how would you make it match if they had done it the good old-fashioned quotient rule way? Common denominators, putting the fraction together, simplifying, and then it would be your chain rule answer. So right now, it's all these little nice little dainty pieces because you split it all apart. So in some ways, this is nice because all the little pieces are nice and easy, but the problem is it wouldn't look like a big old quotient rule, single top with single bottom, unless you either did the quotient rule and not the ln's, or unless you got common denominators. Some of you aren't scared of the algebra. You're like, I don't mind, I'll get common denominators. Some of you are like, I would have rather just done quotient rule. But all of that is a part of making it match, is considering what your answers are and what form they're in as far as how you should have solved. Okay? Now we're, oh, what? Who's this guy? It's the very last example. Who's this guy? He doesn't look like he needs ln's. Let's just go ahead and derive him. Okay, how do we derive? Yeah, of course we bring it down, because as long as the variable has a constant power, is that a constant power? Doesn't the power rule only work when you have a number in the power? That's not a power that with a number. That's a 3 plus x. That's not a 3. So can you bring down anything? Nope. Oh, but we have the other rule. If you have variables in the powers, bulimbu, right? Bulimbu, as long as you have a constant to a variable, then you can go ahead and, wait, constant to a? Ah! We have a variable to a variable. You need to get out a colored pen and make a big old note of this puppy, because there is absolutely no way to take the derivative of a variable to a variable, of an f to a g, without using ln. No. To find d dx of an f to a g, a variable to a variable, a u to a v, the only way to derive is to use ln. But there is no ln. Oh, no big deal. What did we just see? If there isn't one, what do? We make one. So ln of y is equal to ln of 2 plus, ooh, why am I saying plus? I need to get that little x with his little exponent separate from, so get rid of that 2. Got it. Aha. As soon as you get him trapped in an ln, now what can you do? That's not calculus, that's pre-cal, everybody. That's the only possible way to go. So now I have ln of y equals ln of 2 plus 3 plus x. It might not be pretty, but it's possible. And I'll take possible over pretty any day. There's a hidden life lesson in that one, but it would take some work to draw it out. Now I can go ahead. Derivative of ln of 2. 1 over 2 times 2 prime, which is 0. Oh, he's a constant. No stress. We got it, right? Just a product rule. So second, d first, 1 plus first, d second. So dy dx. Move the y. 0 is just 0. ln of x is himself. And what do we do with that little y? Don't distribute. Plug in. I got a couple plug-ins and a few that just kind of kept staring. Suppose you can get a common denominator. It's up to you guys to make it match. That's just algebra. Did you make a note? Did you put some sort of colored, highlighted something or others around it? Maybe we should even put it on a forever card. I don't know. I'll think about it. But the only way to derive a variable to a variable, this guy, illegal. That needs to be a constant. This guy, illegal, needs to be a constant. The only way is to use ln. Now you can finish up section 2.5. Now you can finish up section 2.5. You don't need to post another picture on Google Classroom, but have it ready to grade tomorrow with a colored pen. We still have 2 minutes, you slackers. All right, I'll show you. Oh, not there. I'll show you where we're going. Section 2.6. Ah, inverses. Y and solve for y. Dun, 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 dun. Oh, come on. You guys even know how to fill in the blanks, right? Because inverses, where do they reflect across? Think ln and e. What is this line? That's a parabola. What line is this? Identity, isn't it? Who's the identity? Y equals? Switch x and y, solve for y. Not a reciprocal. Who is it? F. Inverse. Yikes! -1. No, it's F inverse. What's true if you take a composition of a function with its inverse or an inverse with its function? What always happens? What happens if you plug a square root into a squared or a squared into a square root? You get back to? Square one. They are their own undoings. Ooh, they undo each other. Domains and ranges switch, so the x's and y's. That's all pre-cal, everybody. Tomorrow, let's figure out what the calculus is. Bye.
I didn't post that on the website. Should I just go take a picture?
Great. Thanks. Ryan, go ahead and post a comment if you're like, I didn't know, I couldn't figure it. That's okay.